Okay, remember last class we learned about Taylor polynomials, and we learned how to find them in the formula for finding Taylor polynomials. So let's review that formula. Remember, if we want to find the polynomial of p of n of x, that would be f of a plus f prime at a times x minus a plus f prime, double prime of a divided by 2 factorial times x minus a squared plus f triple prime of a divided by 3 factorial and times x minus a cubed plus, and we go all the way until we get to f, the nth derivative of f divided by n factorial times x minus a to the nth. Okay, what we're going to talk about today is we're going to kind of figure out why we find those polynomials and how are they useful. Because basically when we get some higher level math and some applications, sometimes it's much easier to use polynomials than it is to do transcendental functions in order to find integrals or derivatives or things like that. So what we want to do is we want to approximate a difficult function, say a trig function, with a polynomial, because polynomials are differentiable everywhere, integratable anywhere, so they're nice to work with. So we're just approximating. And remember, A is the neighborhood, the center of our approximation, where we're trying to get close to. So let's find, for our example today, we're going to find P1, P2, and P sub 3, and P sub 4. For f of x, we'll just make it equal to sine of x. So just a simple trig function for us to work with. And we're going to center this at pi over 6. All right, so let's review the algebra that we learned last class. So in order to find, and we're going to go all the way to P of 4. So I need to find my function, and I need to find my first 4 derivatives. So f of x in this problem is sine of x. And now we're going to find the derivative of sine of x, which is simply cosine of x. Then we're going to find the second derivative of which is negative sine of x. The third derivative, which is negative cosine of x, and one more derivative, the fourth derivative, gets us right back to sine of x. So now that we have our derivatives, let's evaluate each of those at our center, pi over 6. So f at pi over 6 gives us sine of pi over 6. From our unit circle, we know that's 1/2. Then f prime of pi over 6, that's cosine of pi over 6. We also know that's square root of 3 over 2. And then the second derivative at pi over 6 would be negative sine of pi over 6. Well, we already know that sine of pi over 6 was 1/2, so that's going to be, we already know that sine of x is 1/2, so this is going to be negative 1/2. And negative cosine of pi over 6 gives us negative square root of 3 over 2. And last but not least, fourth derivative of pi over 6 gives us back to 1/2. So let's find P1. Okay, so P1, we take our f of a plus f prime of a times x minus x minus a. And so in this case, our f of a is 1/2. We figured that out, top of the second column up here. Plus our derivative, which would be square root of 3 over 2, times, in parentheses, x minus pi over 6. All right, so now let's take a moment to go to our graph and let's look at what that function looks like. Okay, so here is the sine curve, and we want to approximate this curve near the point pi over 2 comma 1/2. So this point here on the graph. So we want to focus in. So remember, with Taylor polynomials, we're trying to approximate what the curve looks like near that point of interest. With polynomials, because transcendental functions are hard to do calculus with sometimes, but if we did polynomials are differentiable everywhere, integratable anywhere. A lot of rules work nice and pretty with polynomials, and they're easy to work with. So we're trying to find a polynomial to represent this. We have just figured out P1. And so if I look at P1 here, it's just a linear equation. And notice that it's, if I look at the endpoints, I look around pi, negative pi, and pi is pretty far off my curve. But if I zoom in near that point of interest, I can hardly, right really close to that point of interest, my blue graph, which is a line, is right on top of my trig graph. And so it's a good representation when I'm extremely close to pi over 6. Okay, now let's look at our second polynomial approximation, so P2. So P2 is going to be our f of a plus our f prime at a, x minus pi over 6, and then that's all the same. So the first two terms are the same as P1. Now this time I want to take my derivative at the second derivative over 2 factorial times x minus pi over 6 squared. Let's simplify that down. Just make it a little bit neater. Negative pi over 2 divided by 2 factorial is just negative 1/4. Okay, now let's go back to decimals and see how this approximation compares to our P1 approximation for sine of x. Now we're going to use our second approximation. We went to 2 degrees, so our P2 approximation, Taylor approximation, will give us an even better estimate of this blue linear line. So here I did it in red. So this is my P2 Taylor approximation, my Taylor approximation when n is 2. And notice that red line stays close to the black curve of this y equals sine of x much longer than the blue. As you can see, it's closer to the curve. It's more close, and while we're in that near that pi over 6, but we can be a little bit farther away from pi over 6. We don't have to zoom in as much. So let's go figure out what P3 would be. All right, let's go to P3. So P3 will be P2, so we can go ahead and just copy P2 all the way down. And then our last term is going to be plus our third derivative, evaluated at pi over 6, which is negative square root of 3 over 2, divided by 3 factorial times x minus pi over 6 cubed. So let's simplify that last term. And we get the square root of 3 divided by 12 times x minus pi over 6 cubed. All right, let's go to decimals and compare our green graph to our red graph. Okay, so now that we found P3, so let's go ahead and I'll do P3 here in green. So green here is my Taylor approximation when n equals 3. So you can see that is even a better approximation. So let's zoom on in here and see, let's take that linear one off, and you see that in fact, on most of the part of this graph, it's hard to tell where the black and the green end. So they're pretty darn close. So this is a much better approximation, much better than that red that was so far off. So we can get a little bit farther from that center point. We can use more values we can work with here. Okay, so let's see what would happen if we go to P equals 4. Okay, our last one, let's find P4. So that's going to be P3. To find our last term, we're going to do plus our fourth derivative divided by 4 factorial times x minus pi over 6 to this 4th degree. Simplifying the final term, we end up with 1/2 plus the square root of 3/2 x minus pi over 6 minus 1/4 parentheses x minus pi over 6 squared minus square root of 3/12 x minus pi over 6 quantity cubed. And then the last term is going to be plus 1/48 x minus pi over 6 to the 4th degree. Let's see what that graph looks like. Okay, here is your P equals 4 approximation. Okay, now you'll say, wait a second. Over here at the ends, that purple is farther from the black line than the green. But over here, the purple's on the right-hand side, the purple is closer to the green. That's going to happen because, we're looking at these polynomials. But notice if I zoom in near where they start diverging, here notice that the purple stays closer to the black. Here the black is really, really close. And now let's see, the purple is closer to the black until about here. Now we're starting to get about equal spacing from it. So the purple stays a little closer to it. So it is a little bit better estimating of this. But that's pretty much all we're doing with Taylor series here, is we're using this to approximate that sine curve. And you can see it does do a pretty good approximation of that sine curve. It's just that when we get farther and farther away, it starts getting really far off. So you can see how we got closer and closer in that neighborhood of pi over 6, the center of our interest, our area of interest. We get closer and closer the higher the degree. So this gives us a better approximation. And we can go to p equals n, and we'd get even farther, and you chase this out and get farther and farther and farther, and you get a better and better approximation of this curve as you go along.